All right, here we go. So today we're going to learn about work done by non-conservative forces. All right, this is basically our third lesson, I guess, on how work and energy kind of relate. All right, so at this point we've already learned two really important things about how work sort of affects the energy of a thing, right? So the first fact that we learned was this. We learned that the work done by conservative forces is equal to the opposite of your change in potential energy. So for example, if you calculate the amount of work done by gravity, that's going to be equal to the opposite of the change in potential energy. So if gravity does positive 10 joules of work, then you lose 10 joules of gravitational potential energy. All right, so that's the first sort of work and energy relationship that we learned. All right, the second one was the work kinetic energy theorem, right? In which we learned that the net work, if you calculate the total work done by all forces acting on your object, that's equal to the change in kinetic energy. All right? So the piece that we haven't learned yet, and that is the point of today's video, is this. What's going on with the work done by non-conservative forces, right? How does that affect the energy? All right, and so to answer that, here's what we're going to do. So every force can be described as either conservative or non-conservative, right? So let's do this. What if we looked at the work done by non-conservative forces combined with the work done by conservative forces? Well, isn't that everything, right? Because every force is either conservative or non-conservative. So when I add those together, that's giving me my net work, right? Because every force is conservative or non-conservative. So if I add those up, I've calculated everything. That's all the work that we could have done, right? Okay, so now what I'm going to do is I'm just going to do some substitutions, okay? So I'm going to leave this. This is the thing we don't know about, but we know something about these other two guys. So let's see, the work done by conservative forces, well, that's just the opposite of my change in potential energy. And again, I'm using U for potential energy now, right? Okay, and that's equal to my net work. Well, my net work is my change in kinetic energy. So if I add change in U to both sides, then I get this. I get the work done by non-conservative forces is equal to my change in U plus my change in kinetic energy. Oh, that seems, that's a thing, isn't it? Right? That's our total energy, right? Okay. Ooh, neat. We just learned a thing. The work done by non-conservative forces is equal to, well, there's only two types of energy that we talk about, right? Potential energy, kinetic energy. So that's everything. So it's our change in total energy. All right. But this year we're not going to talk total energy anymore. This year we're going to talk about mechanical energy. All right. Because there are other types of energy besides potential and kinetic energy. There's also what is called thermal energy, heat in English, right? When something gets hot, that's a form of energy, right? So we are no longer going to call this total energy. I'm going to try to get better about this. We're going to call it mechanical energy, E-mech, mech being short for mechanical. All right, so what we had previously referred to as total energy, we're now going to call mechanical energy. And then we've got this additional form of energy, which we're going to call thermal energy, which is heat. Okay? All right, so we just got two things out of that little segment there. One, the work done by non-conservative forces is your change in total energy, mechanical energy. All right? And we also need to talk about heat. All right, so heat. Well, where would heat come from? I'm going to think for a minute. My hands are getting hot. Friction produces heat. So, where does friction fit into all of this? Well, so it turns out, and there's not a whole lot to this, it turns out that as a non-conservative force, there's nothing special about static friction. Okay? Static friction just allows the contact of one object to move another object, right? There's static friction between my hand and the pen, that's what's causing the pen to move. All right, but for kinetic friction, because your surfaces are sliding across each other, that can produce heat, okay? I'm causing the molecules in my hand to vibrate faster, which produces heat, okay? So it turns out that if you calculate the work done by friction, that is equal to but opposite the change in thermal energy. Right? When I rub my hands together, friction is working against me. So friction is doing negative work, and as a result, I'm gaining heat energy as my hands get hotter. Okay? So this is a minor relationship, but every once in a while they throw a problem at you that's about thermal energy, and they're basically just asking you for the work done by friction. Okay? Those are the two things that we need to know. Work done by non-conservative forces is equal to the change in mechanical energy. And the work done by friction is opposite the change in thermal energy. Okay? So how can we use this? So probably the easiest way to use this is just by doing an example. This answer here is not right because I changed the problem, but did not change the answer. Okay, so pause the video here and take a second and scribble this down. All right, we got a 3 kilogram block. It's going to be launched up a frictionless inclined plane by a spring as shown in the figure. The plane is inclined at 30 degrees to the horizontal. The coefficient of kinetic friction, wow, I did a rotten job editing this. We're going to go frictionless, right? That's why it says frictionless. All right. So the plane is inclined at 30 degrees, and the spring constant is 490 newtons per meter. All right, so in part A, what we're going to do is we're going to slowly press the block against the spring to compress the spring another 0.2 meters before the block stops again. And the question wants to know how much work you're doing. So I guess the question, why did I say to compress the spring another 0.2 meters? Well, we're moving the block, right? So there are two sort of positions that we care about. There's the starting position, and then what happens after we compress it. So our starting position is this right here. But notice, because the block is already touching the spring, the weight of that thing is already compressing the spring by a little bit, right? So that feels like it's relevant. So let's take a quick second and figure out what that looks like. All right, so as this is shown, let's call this point, let's call this point R, as in at rest, R for rest, okay? So at R, should we use capital R? I used lowercase r in my notes, so I'm going to stick with that. Okay, so at this point, what do we know? Well, let's see. So here's our block. And so we know it's a 3 kilogram block, and we're on an inclined plane, so we're going to have to split up our gravity, right? So there's a perpendicular component of gravity, which, if you calculate it, turns out to be a number that I've written on this page over here. We don't actually really need it till later. It turns out to be 25.46 newtons. Which means that we're going to have a normal force, which is equal but opposite. So 25.46 newtons. Some of you are yelling at me about the signs. Go ahead and make that guy negative. All right, and then we've also got this perpendicular component of gravity that's pulling the block down with a force of 14.7 newtons. And that's what's causing the spring to get squished a little bit, right? And in this image here, right here, it's not moving, which means our net force is 0. That means that the force of the spring must be positive 14.7 newtons, right? Okay, so based on that, we ought to be able to figure out how far our spring has been sort of compressed, right, from its relaxed state. So here's the relaxed state. Here's our rest point. Those both, unfortunately, begin with R. So here's our XR, right? It's the distance that it got compressed until it got back, until it was at rest. So let's see. Force of spring is negative K times XR. So our force of the spring is positive 14.7. Our spring constant is 490. I'm being sloppy about units, newtons per meter, times XR. So solve it, and your XR turns out to be negative 0.03 meters, which means that just in the drawing, before we even compress it, our spring is already squashed 0.03 meters. All right? So now we can start answering part A, because we're going to compress it another 20 centimeters beyond that. Okay? So, what do I want to do here? Is there anything I need here? I need to keep that XR, but I think that's it. So I'm going to get rid of all of this stuff. Get rid of this. Oh. Still no friction. Okay, so let's call the next point, let's call it S for squashed. Okay, so the idea is now we're going to take our block and we're going to compress the spring. So the spring has now been compressed another 0.20 meters on top of the 0.03 meters that it had been compressed before. Okay, so the question wants to know how much work you are doing. All right, so the idea is while you're compressing the spring, while you're squashing that weight down there are three forces that we care about, right? Three forces sort of in the direction of motion, okay? There's FG parallel is pulling down the hill. There's the force of U squishing this thing, or squashing, if you prefer. And there's the force of the spring, right? Okay, so we're trying to figure out how much work you're doing. Now, I guess the first thing we could do is if we could somehow figure out what the force that you are exerting is, we could then just do force of U times 0.2 meters. But the problem here is that the force that you're exerting is not constant, okay? And as a result, we can't do that, okay? If we could find the average force we exerted, then we could do that. We could do average force times the 0.2 meters, and that would work. And in fact, does work. But that doesn't help us learn the concept that we're trying to learn here, okay? So, check it out. We are trying to find the work that you do, okay? Well, that's a non-conservative force, right? What are the other forces? Well, there's the spring, that's conservative. And there's FG parallel, also conservative. Oh, so the work that you do for this problem is the work done by non-conservative forces because you're the only non-conservative force. Oh, well, that's got to be equal to our change in mechanical energy, right? Okay, well, so that is the change in potential energy plus the change in kinetic energy, right? All right, so let's see. So it starts at rest. It was at rest before we squashed it, and then we squish it until it stops again. So our change in kinetic energy is 0, but we do have two types of potential energy. We've got a change in gravitational potential energy plus a change in elastic potential energy, right? Okay, so if we can figure that out, then we figured out how much work you've done, right? So, let's see. So change in GPE, let's deal with that first. So, sorry, wandering around over here. So change in GPE. So the idea is we've got this, this ramp, and we're going to smush the box so it goes down the ramp a distance of 0.2 meters. But since this is 30 degrees, you can do 0.2 times the sine of 30 and figure out that your change in height is negative 0.1 meters, right? Because it's going slantways down 0.2 meters, and so the vertical displacement is negative 0.1. So our change in GPE is just mg delta h. So the mass is 3 kilograms. G is 9.8 meters per second squared. The height is negative 0.1 meters. Multiply this whole thing out, and you get negative 2.94 joules. So that's my change in GPE. All right. So now we need to figure out what's our change in elastic potential energy. And unfortunately, there isn't sort of a shortcut we can take for finding change in elastic potential energy. Our change in elastic potential energy is just EPE final minus EPE initial. So let's go back up for a second. So before we did anything, it was already squished 0.3 meters, right? And then after we compressed it, then it was compressed 0.23 meters, right? The 0.2 that we squished it plus what it had already been squished. Okay, so here we go. So this is 1/2 times k times our final x is 0.23 meters. Don't forget to square it. Oops, I want minus. So that's my final elastic potential energy minus my initial. All right, and plug that into your calculator, and you get 12.74 joules. So when you squish it, you lose this much GPE, you gain this much EPE, and so going back up to here, that means that the work that you did is equal to our change in total energy, which in this instance is just GPE and EPE, right? So, sorry, my board's getting totally cluttered here. So the work that you did, to recap, that's equal to the work done by non-conservative forces. That's equal to the change in mechanical energy. Well, the only types of energy that change are GPE and EPE, right? There's no friction, so we don't need to worry about heat, which would be a non-issue, so pretend I didn't say that. And there's no change in KE because you start net rest. So this gives you negative 2.94 plus 12.74, which gives you 9.8 joules of work that you did. Kabam. All right? Now, a quick side note. We could have solved this by using the network thing, right? So network is our change in kinetic energy, right? So that means the work done by you plus the work done by gravity plus the work done by the spring is the change in kinetic energy. But watch what happens. If you do this, it ends up being the exact same thing we just did, right? Because the work you did is the thing we're trying to find. The work that gravity did is the opposite of the change in GPE. The work the spring did is the opposite of the change in EPE equals change in kinetic energy, right? And then if you add, you get what we did, right? The work that you did is just the change in total energy, right? It's the change in GPE plus the change in EPE plus the change in KE, which we had already established as just 0, right? So, all right, so that is that. All right, now, part B. Suppose you release the block. So we've squashed it, those 0.2 meters. Now we're going to release it and sort of let it slingshot up the ramp. So the question wants to know how far above the spring's relaxed state the box will go before stopping. Okay. So I'm thinking about 2 positions here. So there's the squashed state, right? And then ka-chunk, you let it go. It's going to go past the relaxed state. And it's going to keep going up the hill. We want to find that distance there, right, until it stops. Okay, so let's do this. Because we're dealing with GPE, we need to find, we need to sort of determine our point where our height is 0. So let's call this point a height of 0. So here our height is 0, our velocity is 0, but our spring is squished 0.23 meters, right? Then ka-chunk, it goes to up here. Now when it gets to up here, we're going to have some height. The spring is no longer squished, and it stops again, right? Oh, so what that means is, at this starting point, I've got just elastic potential energy, and at my ending point over here, I'm going to just have GPE, right? Now, are there any non-conservative forces? Well, after you let go of it, the only forces are the spring pushing it up and gravity pulling it down. So my total energy here ought to stay the same, right? You could think about it this way. the work done by non-conservative forces now is 0, which means my change in mechanical energy is 0, which means my total energy has to stay the same, right? So at the bottom point, I've got elastic potential energy, 1/2 times K times X equals the GPD at the top, which is the mass times 9.8 times the height at the top. Let's call that HT, so we're not reusing a variable. Okay. Oh, well, that means then that the height at the top, if you solve this mess, the height at the top gives you 0.441 meters. So that's this height right here. So a little bit of trig tells me that the hypotenuse of this triangle is twice that, right? Because it's a 30, 60, 90 triangle. So this is 0.882 meters. But we're just looking for D. We're just looking for this chunk here, right? So we got to subtract out the 0.23 meters, right? So 0.882 meters minus the 0.23 meters we had originally squashed the spring, and that gives you 0.651 meters. Bam. All right. So what's significant about this problem is there aren't any non-conservative forces. All right. So for part C, let's go back and do this again. But when we do it again, what we're going to do is this time we're going to take into account, we're going to ask ourselves, what if there was friction? Okay, so we're going to do the exact same thing we just did, but this time there's friction on the ramp, but only above the relaxed point of the springs. All right. Okay, so there's kind of 4 points that we need to think about here, right? So here's the ramp. So there's the point down at the bottom where we had already squashed the spring, after we applied our force on it. There was the original rest position where just the weight of the box was compressing it. There's our relaxed point. So we can put some numbers in here. So this distance was 0.03, you may recall. And this distance is 0.20. So what we're going to do is we're going to compress it. We're going to spring it up the hill. It's going to go all the way up to here to some highest point, which we will call top. And to be clear, there's friction here. Okay, but just above the relaxed place. Okay, and so what we're trying to do is we're trying to find this, how far it goes. So let's call it XF, as in X that goes with friction. All right, so that's what we're looking for. Okay, so let's smallify our drawing here a little bit. So that we can kind of save some space here. Well, and apparently we're smallifying the problem too. So there we go. Oh man, Smartboard is not cooperating with me this afternoon. Okay, so what do we know? Well, at this point down here, we had decided previously that we were going to call that a height of 0. We knew that the velocity was 0. The spring had been squished. And so we had calculated our elastic potential energy before. And it was 12.9605. Why is that number not familiar to me? Oh, just because I didn't write it down. Okay, so 12.96, let's just call it 12.96 joules. Okay, now, when it gets to this point, the total energy has now changed, right? Because we've got now a non-conservative force. So as this thing is moving, what force is acting on it? There's gravity, that's conservative. There's the spring, that's conservative. And there's friction. So what I know then is between my red point at S and my top point at T, I know that the work done by non-conservative forces is equal to my change in, I said total before, I should have said mechanical energy. Okay? So that is equal to my mechanical energy at the top minus my mechanical energy down here where it's squashed, this S point. All right, and that's equal to the work done by non-conservative forces, but our only non-conservative force is friction. So the work done by friction is equal to that. All right. So I guess we need to go off to the side and make a little free-body diagram. So we'd already kind of done this before, right? So here's our box. We had our FG perpendicular, which we had decided was 25.46, which meant that our normal force was 25.46. So now we can find our force at kinetic friction, right? Just by doing coefficient 0.4 times our normal force. So if you do that, you get negative 10.2 newtons. So there's our force of friction, 10.2 newtons. Okay, so the work done by friction, well, that's the force of friction times the displacement that it goes through. So force of friction is negative 10.2 newtons down the hill times the distance it goes up the hill. So that's the work done by friction. All right, let's see. Now, my mechanical energy at point T, well, that's just GPE, right? So that's the mass of the box times 9.8 times some height minus the energy we began with, which is this 12.96. All right. So now all that remains to do is to find a relationship between XF and H. So here's my XF. If you draw your triangle, then this is H. So it's a 30, 60, 90 triangle. So this hypotenuse here is XF plus 0.23, right? So I think then that H should just be 0.23. That was how far, that's how far we squashed the spring, right? Plus X all over 2, right? So if I take this equation then and substitute this in for H, then I can just solve and I'm done. So what do we got? We got negative 10.2 XF. Oh, this is supposed to be XF, sorry. Equals, let's see, 0.3 times 9.8 is 2.94 times H minus 12.96. All right, and solve this. And so if you solve, we end up getting 0.343 meters. All right. But the big thing that I want to make sure you guys understand here, that I'm worried that I did not emphasize enough, is the whole, all we did there was we said, all right, well, we got 2 points, you know, our starting point and our top point, and the only non-conservative force acting on the object between those 2 points is friction. And so the amount that my energy changes between here and here is just equal to the work done by that non-conservative force of friction. All right. Also worth noting, now that we know the work done by friction, right, if we go back and plug our X in, notice the work done by friction is negative. And so what I probably should have done then is said, find the gain in thermal energy, right? Well, it's just, you know, the opposite of your work done by friction. So, you know, you just plug this in up here to find your work done by friction. That gives you negative, what, negative 3 point something, which means the gain in thermal energy is positive 3 point something. All right, there we go.